So hello and welcome everyone to the course Industrial Robotics and Automation. In today's lecture, we'll be dealing with the topic hydraulic circuit design. Okay, so before starting the hydraulic circuits, okay, first let us get used to these terminologies, that is your single acting as well as your double acting cylinders. Although I had a brief discussion about it in my second class, but today again we'll first just go through the symbolic representation of each, and then we will go into your circuit diagrams involving these two types of cylinders. Okay, so the picture to the left of your screen denotes your symbolic representation for your single acting cylinder. Why is it called single acting cylinder? It is because you have one port that acts as a pressurized inlet port, and your cylinder extends due to this pressurized inlet port. Okay, the retraction is through your spring. Okay, so you do not have to have any other pressurized port from the other sides. So that same port acts as your pressurized port during the extension, and it acts as a drain port when the cylinder retracts. Okay, and what is the force of retraction? You do not have any fluid pressure. Instead, you either have a spring force, or it is the weight of the object itself that is either lifting, okay, or any other force that it is actually expanding during your extension stroke. Okay, so either by the force of the by the weight or the force of the actuating whatever load it is that taking place, that, or through your spring return mechanism. Okay, so these are the two ways through which it returns, and its symbol can be seen here. Okay, and to the right of your screen you can see a symbolic representation of a double acting cylinder. Okay, so why is it called double acting cylinder? Again, because there are two ports, and both the ports acts as a pressurized port as well as a drain ports. So during extension, okay, in this case your left port will be acting as a pressurized inlet port, okay, and your right port will be acting as your drain port during the extension of the cylinder. Whereas for the retraction of the cylinder, again your right hand side port will be acting as a pressurized inlet port, and your left port would be acting as your drain port for the cylinder to retract. Okay, so these two are the symbolic representations of your single acting and your double acting cylinders. We will be using these two very much often, okay, in your hydraulic circuit as well as in your pneumatic circuit. Okay, because symbolically there is no difference between the two. Okay, whereas there is a vast difference in the construction of a hydraulic cylinder and a pneumatic cylinder. Of course, all your components that will be used for a hydraulic cylinder would be able to bear a much higher pressure, because generally the hydraulic cylinder operates at a very high pressure, tentatively ranging of upwards of 150 or 200 bars, whereas your pneumatic cylinder operates between your general pressure of around 5 bar to your 10 bars. Okay, so again all those component cylinder walls and all those linings and all, they will be less strong as compared to that of your hydraulic cylinders. But again, the symbolic representation for both would remain the same. Okay, so with this we will be first seeing how to control a single acting hydraulic cylinder. Okay, so in today's class we'll be dealing with all the circuits related to your hydraulic portion, right? So for the hydraulic portion, again you must be thinking, since just a few minutes ago I told you the symbolic representation of your cylinders would remain same, okay, for your hydraulic and pneumatic, then why am I saying that this is a specific circuit diagram for a hydraulic cylinders? Okay, so basically your representation for your actuators, that is the cylinders, and your valves, okay, would remain the same for both hydraulic and pneumatic. However, all your power generation systems as well as your different safety elements that are there, okay, it is specific to a hydraulic system, okay, that may differ, and for a pneumatic system it would again differ. So in today's lecture we'll be covering only that of your hydraulic system. Okay, so now if you can just recall from the previous class, this is what is your single acting cylinder, Okay, then what is the type of DCVs that is here? What is the type of DCV? Okay, it is a 3 by 2 way. Why 3 by 2 way? Because it is a 3 port, 1, 2 and 3. Okay, similarly you can see 1, 2 and 3, and 2 positions. If you can see, you have 2 positions. Okay, this is your default position since all your connections have been made here, and this is your actuated position. Okay, how is it offset to a default position? How the default position is maintained? It is spring offset. If you can see, this is the symbol of a spring. I told you some has to be, it has to have one default position, and that default position has to be maintained by some mechanism. Okay, in this case it is a spring offset, and the third terminology what you are going to do is what is the actuation mechanism for it. Okay, so in this case it is a manually actuated. So it is a 3 by 2 way spring offset manually actuated DCV. Okay, what are your power generation elements in this? If you see the lower one, this is a symbol of a reservoir. Okay, so you have your reservoir here. Okay, this component to the bottom most of this diagram. Okay, this is a reservoir. Then comes your strainer or your filter to filter out the oil. Okay, when the oil is getting sucked from the reservoir to your pump, this is a pump. Okay, this is your pump, and this triangle at the end of the pump here, this shows your pressurized line from here onwards. Okay, so that means from here onwards all these lines will be pressurized. Okay, that is your output of the pump. When you compare it to your pneumatic circuit, okay, then these elements would not be there in a pneumatic circuit. That is your reservoir, strainer, okay, and your all this pump would not be. You will be directly having a pressurized element, that is will be your output of your compressor. So we'll directly start a pneumatic circuit with this small triangle here. Okay, so that means this whole portion would be a part of a pneumatic circuit. Don't worry, we'll be covering the pneumatic circuit in detail, okay, from tomorrow onwards. So for today you can just be focusing on your hydraulic circuit diagrams. Okay, apart from this, you can say this is a single acting cylinder here, this is a valve DCV. Okay, and then this is your power generation from here. Okay, that is your comprising of your reservoir, strainer and your pump, and of course this pump will be driven by a motor. Now if you can see, what is this feature here? What is this? Okay, this is what is a safety device. Okay, and that is your, it is known as relief valve. If you can again recall from the previous lecture, what type of control elements you had? First of all, you had a control element that could actually control the fluid path, known as your DCVs. Second was your speed control elements, right, which could actually control the flow rate and detect and determine the extension or the retraction speed of the cylinder, or your clockwise and anti-clockwise rotation of a hydraulic motor or a pneumatic motor, that is a rotary actuator. And the third element was your pressure control elements, right, which actually controlled your pressure or your regulated your pressure. Okay, so this is one of that element. It is known as a relief valve. Okay, how does it work? Now suppose when your left portion of your cylinder is actuated, okay, that is, okay, this portion of your valve, okay, is actuated, then your cylinder extends. Now suppose your cylinder has extended, and again when you have put in this default position again back, then your cylinder retracts. Okay, now suppose it has retracted, and in the next cycle there is a time delay in the next cycle. Till that time this pump is running. Okay, say your entire system was to work at 150 bar pressure. Okay, so now you see in the default position, what is this? This port is blocked, right? If this port is blocked, that means your pump would still be running and there is no flow of liquid. That means your, in this portion, in this line, okay, of your circuit, pressure would start building, right? Now this, as the valve says, it is a relief valve. That means once you set a certain pressure, after that, beyond that, the pressure will not go, it will get relieved. How will it get relieved? Say you set a relief valve pressure of, say, suppose 160 bar. Then what would happen? When this port is blocked, okay, pressure would start building here, and it will also build in this line, since this line is connected. Okay, I told you this dotted line is a pilot line. That means it actually, the pressure starts to build here. Okay, this is one two-way valve here. Okay, this is the inlet of that valve and this is the exit port of that valve. Okay, and the spool is generally not aligned to this inlet and outlet. It is generally kept as some offset, and that is actually engaged through some spring pressure here. Okay, so you can just tighten your spring and put amount of that tightening and loosening of spring is actually determining your safety pressure. Okay, so you can set, if you if you just tighten the spring, that means you are actually increasing the pressure, relief pressure. It may go up to say 180, 190, 200 bar, and if you loosen it, it may go suppose 20, 30, 40, 50. So it depends upon how much spring force you are applying to just put this spool in an offset position. Okay, now say this spring is putting this spool to an offset of, say it is keeping it to an offset of 150 bar. Now the moment in this line 150 bar pressure rises, okay, it rises up to 150 bar, then what would happen? The spool would shift towards top, okay, and your this inlet port would get connected to your outlet port, and then your pressurized fluid will start to drain. Okay, and this is the reservoir here. So that means it would start to drain, but will the pressure drop in the system, or will it be maintained at that relief valve pressure? It will be maintained at that relief valve pressure. Why? Because the moment the pressure decreases, what would happen? This spring force, okay, would again push the spool back to its normal position, and then you will not have any flow between the inlet and the outlet valve. That will be the case when suppose the moment you actuate this portion of your extension portion of your valve, and your cylinder starts to extend. That means again you are having a normal pressure. But say suppose again this cylinder reaches its extended position, and then you are keeping the lever in its engaged position itself, and the cylinder has extended completely. Then again what would happen? Again the pressure would start building in this line. Okay, because your cylinder cannot move any more forward and your pump is still running. So then again this would act like this relief valve would actually relieve the extra pressure, okay, by just opening this valve and draining the liquid from your this inlet to your outlet port. Okay, so this is a relief valve, and it actually protects the system against any exorbitant increase in the pressure. So whatever pressure you will be set, it would always make the pump to run either below or up to that pressure. Okay, so this is a relief valve or a safety device that is actually put here. Fine. Now let us see the control of a double acting hydraulic cylinder. Okay, so again this is a double acting cylinder. Okay, you can have here you have one port towards the upper side and your lower port is here. Okay, that is your another port, that is the second port is denoted here. So you are having two ports. Okay, and this is a symbol of a double acting cylinder. Okay, now again in between you can see a valve. So what type of valve is this? If you see, it is a 4x3-way valve. What do I again mean by 4x3-way? It has 4 ports. If you see 1, 2, 3 and 4 ports. So the first one is a pressurized port. This one is your tank port, okay, or the port that actually links it to the reservoir. And you have 2 connecting ports, that is your A and B ports, to be connected to the 2 ends of a double acting cylinders. Okay, so you have 4 ports here. Okay, that is why the first letter denoted by before your hash is your numeric value actually denotes your ports, and the second numeric value after the slash determines your position. So if you see, there are 3 positions. This is the first position that will be like actually extend the cylinder. The second position in which all the ports are blocked and the cylinder would remain in its whatever position it is there in, and this is a third position, that is a retracting positions. Okay, so you have 3 positions denoted by 3 square blocks here, and you have 4 ports. Then what is it? It is spring centered. If you see, both springs are there, okay, 2-way centers. That means till when you are actuating it, actuating force is applied, it would either extend or the retract the cylinder depending upon which side you are applying the force. The moment you just move the lever, the valve will come back to its center position since it is spring centered. Okay, and then you can say it is manually actuated because these are the symbols of a manually actuated through lever mechanism. Okay, so it is a 4x3 way spring centered manually actuated valve, right? Then again the power generation will again consist of the same things here. So you'll be having a reservoir, your strainer and your pump, right, which is actually driven by a motor. After that, you also have your safety device here, which is your relief valve, as we discussed in case of your uh, control of a single acting cylinder. However, one extra element can you see here. Okay, what is that? This element here. And if you recall from your previous lecture, what is this element? It is a check valve, right? Check valve. What is the function of a check valve? It is also known as your non-return valve. That means, or a one-way flow valve, which actually allows the flow through only one direction. In this case, what would be the direction? From bottom to the top. That is connecting your pump outlet to your valve inlet. That means your flow can only be like this, through this way, and your flow cannot be the opposite side. Okay, it cannot be from the, say, your valve. This is your DCV, na, from DCV to your pump. Okay, why is this called a safety device? Again, say suppose I am extending a double acting cylinder. Okay, I have calculated all my load calculations, and from there I can say that whatever is my load, to extend that load I require a pressure of, suppose, say 150 bar, right? And I start extending the cylinder. Okay, so the cylinder, I just engage my valve to my left envelope here. Okay, that is this envelope, and my cylinder starts to extend. Now see, imagine there may be two cases. One, somebody has wrongly calculated the load. Okay, so suppose according to your load, he selected 150 bar pressure, right? But actually the load is a much greater load and it requires, say, suppose 180 bar of pressure. Okay, so what would happen? Your cylinder, or say it is a dynamic load. Okay, so initially the cylinder is extending, okay, that load is there, but the moment the load increases, then what would happen? If you see, this is your extension line through which your liquid extends and it is coming back from here. Okay, but say suppose if it backfires, that is the load is very much high and your pump is, you did not calculate it correctly, what size of pump, then what would happen? The cylinder, instead of extending in this position, it starts to just push back and retract, and what you will have a liquid that will actually backflow through this and come back, and it will try to enter your pump. But if you have a check valve here, okay, then what would happen? Since this check valve allows your fluid to flow in only one direction, you will not be having any backflow of your cylinders. Okay, the second scenario is what? Suppose you are extending the cylinder and there is a power failure. If there is a power failure, that means what happens? Your pumps get cut off. Why? Because the pump is driven by a electric motor. Okay, so the electric motor stops and your pump stops. That means again, as the cylinder is extending forward, okay, suddenly in between the extension stroke is not completed and your power, there is a power failure, then what would happen? Your pump would stop and then the cylinder would try to retract back because of the load. Okay, so in that case, again, your check valve, even if the cylinder is only half extended or 3/4 extended, okay, and then there is a power failure, it would just try to hold the cylinder in that position itself, because the fluid, while trying to coming back from this line itself, your energizing port, it will not be able to flow in the backward direction. Okay, since the check valve only allows a flow through one motion, that is from, in this case, from bottom to the top. Okay, no motion can be, or no flow can be allowed from your top to your bottom. So this is also acts like a safety device. Fine. Now this is one more type of circuit that is very commonly used, okay, in a hydraulic circuit design. Okay, hydraulic based automation. So this is known as your regenerative circuit. Okay, what is different from the previous circuit? If you see here, this is also a double acting cylinder, okay, and all your power generation units are here, your relief valve is here, okay. Now just try to focus in this portion, okay. If you see this, this is a valve, it is a 4x3 spring offset, sorry, spring centered manually actuated DCB. This is also a 4x3 spring centered manually actuated DCBs. You have your power generation units here, okay, they all remain the same, and then you have your relief valve also here, you have your double acting cylinder. What is the changes here? The changes are to the ports, if you see. So this is showing your default position of the ports, okay. So in the default position you can see this port is right now blocked, okay, this port is also blocked in the default position, that is internal. However, in your extended position this port can be opened here, but if you see this portion, okay, your double acting cylinders in the previous example, the two ports of the double acting cylinder, one is this port and the other port were actually your were connected to your A and B ports of your 4x3 way DCB, right? In this case, there is only one port that actually connects your double acting cylinder, the other port is blocked, okay. So how would the, again, since the cylinder has to extend, so there has to be a return flow of fluid only then. So what would happen? The return line is actually fed to your, again, pump flow itself. So if you see the pressurized fluid discharge, okay, is discharge returned to the system. That means when the cylinder is extending, now just say this is your extending envelope of your valve. So whenever you will be putting the lever forward, okay, to engage this envelope of your valve and your cylinder extends, then what happens? Your pressurized port gets connected to your A port here, and this arrow is connected, so your cylinder starts to extend, okay. And then in a traditional manner, what would happen? This return port would have actually gone here and your fluid would have returned like this, okay. But in this case, in a regenerative circuit, you have your one port block of a 4x3 valve, okay. So you have this port block. Instead, the return line, okay, that is a fluid that is getting drained out from here, is actually connected to your system here also. So what would happen? Your cylinder is extending, okay, and what is the speed by which it will extend? I told you in my previous class, what is this? What element would actually control your speed? It is your volume flow rate, right? It is a volume flow rate, and volume flow rate would actually depend upon what? Okay, area into velocity. Okay, so area is what? The area of this piston, okay, into the velocity at which it extends, okay. So area into velocity will actually be your flow rate, okay. So if you can increase the flow rate, okay, that is the liquid entering from this side, and your area is constant, that means your velocity would increase. Now how would you increase the flow rate? Because for a particular configuration of pump, you have your pressure as well as your flow rate to be as constant as a discharge of a pump. So what would happen? This is your pump flow rate, that is your QP that is going, and then you have your this flow rate that is actually your drained flow rate or your retraction flow rate that is coming and supplementing your flow rate that is there at the outlet of your pump. That means your QT, that is the flow rate that is extending this cylinder, is actually equals to QP plus QR. One is the flow rate of the pump, the second is your flow rate of your discharge fluid that is getting coming and added. So if the flow rate increases, since this area of the piston, okay, is constant, that means your velocity would increase, okay. Now you will imagine what would happen to my retraction motion, because see, for a retraction, what would happen? If you see, this is my retraction valve, okay. So for my this cylinder to retract, until unless my pressure port will not get connected to my B port, that is the other end of the port, my cylinder would not retract. But this port is blocked. So what is happening? I actually bypass the entire DCB for retraction. That means in this case, the retraction port or the retraction envelope of my DCB is not required here. Only your extension would be required, whereas your retraction would be what? The retraction, the moment it is applied there, the retraction would be only from this portion. That means your pressurized line would actually go through this, and it would not go through the DCV. It would go through this, and it would actually just retract the cylinder backwards, and then you can have your drain position here. Okay, so how is the regenerative circuit? You must also have heard right now about your regenerative braking systems that have been used in your automobiles nowadays. So all your hybrid vehicles, okay, that also has a battery to it, in which your during acceleration or during your normal motion, your battery gets charged, okay, or your battery also assists a motor that is actually added to your, apart from your normal torque configuration of your IC engine or the internal combustion engine. So you also have a battery that actually applies some power to it. Okay, so how do you charge the batteries? So when you apply your brakes, okay, so the energy from the brakes is actually regenerated, and that energy is used to charge your batteries. Okay, so that, because see, whenever you are applying the brake, that entire energy is wasted. Okay, so what you do, you harvest that energy, and using a regenerative circuit, you actually use those energy to charge your batteries, so that when you are accelerating, okay, then you can use the battery power also along with the IC combustion engines, okay, internal combustion engines, to uh, drive your vehicles. Okay, so that is also known as your regenerative braking system. Similar is the case here. A regenerative circuit, that means you are using the same energy of that of the cylinder extension, and you are again putting that into a loop during the extension, so that your extension flow rate becomes your addition of your pump flow rate as well as your retraction flow rate. Okay, so this is a regenerative. It only speeds up the extension motion, whereas the retraction motion would just be your normal motion, just like that of your previous example. If you see, so whatever speed in this which this cylinder will retract, in this case also the cylinder would retract with the same speed. Okay, now we will be going up to pump unloading circuit. Okay, so if you can see here, this is again a double acting cylinder with the same type of valves. Okay, now you will be all be getting familiar with these type of terms. So this is again a 4x3 spring centered manually actuated DCV. Okay, then you have your pressure lines, okay, or all your power generation circuits here. And then what is this? This construction is slightly different from that of what you have seen is as your relief valve. Okay, so what is this known as? It is known as your unloading valve. If you can just recall your relief valve, okay, that is okay, this a relief valve. Okay, so in this, what is happening is that extra, that is the whenever your whatever pressure you have set this to, say suppose 150 bar, your pump would continue to work at 150 bar, and only it would prevent extra pressure to get built up in this line. Okay, however, it is not unloading the pump. That means the pump will have to continue to build that pressure of this relief valve, that is 150 bar, and then only then this inlet line is getting connected to that outlet line, and your pump is continuing at 150 bar, and then your fluid is getting drained out. Okay, however, if you want to unload it, why waste so much of energy? Okay, suppose when my cylinder is in the idle position, I do not want to waste the energy, and I do not want my pump to run at its peak capacity or whatever it is to unload the circuit. I just want to unload it so that the pumps run to its zero capacity. Okay, so in this case, if you see, we have actually put this pressure line, okay, which results in opening of this relief valve, okay, or the construction is similar to that of the relief valve, and that I am actually putting it above my check valve here. Okay, so what does this do? This will unload the pump. Okay, since this circuit is a bit, I believe in the past we have seen a circuit that was vertically drawn. In this configuration it is horizontally drawn. So just let me put it here. Okay, so yeah, this in this example you can see it better if you compare it. So now if you can see, okay, here you have your relief valve, and towards your right you can see your unload valve. Okay, now say suppose your cylinder has extended. Okay, once it has extended completely, then what would happen? And it has reached its extended position now. Okay, and you are still engaging this lever in the extended position. Say the operating pressure was 150 megapascal, or say suppose a 150 bar that it is working on, and you have set your unload value to suppose say 155, just a slightly more than that. Okay, so once this cylinder reaches its extended position, okay, then what would happen? Since it cannot move any more further, then your pressure would start building in this line. Okay, it would start building in this line. Once your pressure reaches 155 bar, then what would happen? This 155 bar would also get transferred to this line, and your this entire spool, okay, would get shifted towards left, and it would connect the inlet port to your drain port to this. Okay, and then your pump would start draining. Now see, in this case, since there is a check valve in between, that means between this line, if you see the left figure here, you are pressing one check valve, we are putting one check valve here, and after that check valve we are putting this dotted line, that is the pressurized line here. Okay, so that means your now 150 bar pressure, it cannot go this side. That 150 bar pressure would remain in this line. Okay, and that is also holding your spool towards your center position here. Now your pump could completely get unloaded, and now it does not have to work at 155 bar, for example, pressure to unload itself or to just relieve itself. It will relieve it completely, and this pump will come to as if it is a no loading condition. Okay, however, in this case, okay, if there is any blockage or if the cylinder has extended it completely, okay, then when the pressure starts to build this line, the pump pressure line itself is used to put the spool up, okay, and then connect your inlet port to your output port, and the pump has to continuously build that relief pressure, okay, to put this inlet port and your outlet port connected and drain the extra pressure. Okay, that means in this case your pump will continue to build that relief valve setting pressure. Say suppose you have set it to 155 bars, that means your pump has to work continuously at 155 bar to set. In this case, say the operating pressure was 150 and you set this relief or your unload valving pressure to 155 bar. The moment the pressure in this line reaches 155 bar, okay, then there is a check valve here. That means the pressure cannot flow backwards. The pressure actually goes here and just connects this inlet to your outlet port here, and in this line there is a constant 150 bar pressure because there is no drain line here, and your pump which actually supplies here would now actually go for your draining of this valve, and your pump would get connected to this reservoir here, and your pump would get completely unloaded. Now see, the instant again you shift this or your entire this circuit opens backwards, okay, then again whenever you have your pressure that actually comes below your operating range, then again you can have your fluid flow through this side, because again this would again shift back to its normal position, and then you can have your normal functioning of your valve here. Okay, so this is the difference between a relief valve and an unload valve. An unload valve completely unloads your pump, whereas a relief valve, it only protects the circuit against any extra pressure to be built up, but to obtain that pressure or to maintain that pressure, okay, this pump has to function regularly, okay, and it will never allow your pressure to go beyond that, but however it will function up till that pressure itself. Now let's come back to our next circuit design in the hydraulic system, and it is known as your double pump system. Okay, this is very commonly used in your punching press or all your hydraulic press that is used. Okay, so what is your application of a press? If you see, so your press is something that when the cylinder extends, okay, and say you are having any punching operation, it would first extend and it would not require any load. The moment it is pressing something, say suppose it is forming something or it is punching something, so once it touches that, only then your pressure to deform that part is required. Before that, till when the cylinder does not make, or this position, this load does not make any contact with the workpiece surface here, okay, that time it does not require any high pressure to function. Okay, so in this case what we do, we have a combination of a system. That means we have a high pressure pump. Okay, a high pressure pump would always be a low flow pump, whereas a low pressure pump would always be a high flow pump. Okay, so now in this circuit you can see the use of both your unload valve as well as your relief valve, where your relief valve is there to protect your circuit against any this, and your unload valve will be there to unload your low pressure pump. Okay, when your cylinder starts to start the forming operation or your punching operation. Okay, so initially when the cylinder is extending and it has not touched the workpiece, or your the forming or your punching operation has not started, at that time you will be working with a low pressure pump. Okay, the moment now you have a load, okay, and it tries to press that, okay, then what would happen, your low pressure pump would get unloaded and your high pressure pump will come into your picture and then do your punching operation. Okay, so that means that motion, okay, from the initial retracted position till the position your cylinder does not actually touch the, or your forming tool does not touch the your workpiece, you will have a fast motion of the cylinder, and the exact punching or your forming operation would, the motion would be slow with high application of load. Okay, so see, if you will be just looking at this circuit. Okay, so this is your low pressure pump and this is your high pressure pump. Okay, here it is high flow and low flow. So basically a high flow pump would be a low pressure pump. So see, initially what would happen, this pump would start to run. Okay, and the liquid would go from here all the way through this extending position and the cylinder would extend. Okay, now say low pressure is say during your non-punching operation, say I require a pressure of only 20 to 30 bar. Okay, and my actual pumping or your my actual punching of wood takes place at suppose 150 bar. So that means you have three level of protection here. One would be a 20 to 30 bar at which your generally your cylinder would extend before your actual punching operation starts. Then your punching operation would take around 150 bar of pressure, right? So that would there, and then you also want to make your entire circuit fail safe, so you are putting a relief valve pressure of suppose say 160 bar. That means at no case, okay, my entire pressure pressure in the entire circuit would go beyond 160 bar. However, my operating pressure is how much, 150 bar for the high pressure pump and 20 bar for example for a low pressure pump. Okay, so what I would do, 20 bar would be set at which valve, a relief valve or your unload valve? So 20 bar pressure would actually be set at your unload valve. Okay, and then this entire circuit, the entire forming operation or your punching operation would be done at 150 pressure. However, your relief valve setting would be about some pressure higher than that of your operating pressure. Say in this case, if we are doing it at 160 or 180 bar, so my relief valve pressure would be set at 180 bar. Okay, and that setting we can do with this spring force, right? So now let us see this pump. Okay, this is a low pressure pump and it starts to extend the cylinder. Okay, now the cylinder is extending initially, since there is no load, the cylinder would extend fast. The moment the cylinder stays at 60 to 80% of its extension limit, at that time the cylinder actually makes contact with the workpiece that actually requires a punching or your pressing to be done. Okay, so the moment it makes contact, now what I would require, I would require more force, right? So the moment it touches, what would happen, it would stop initially and your pressure would start to build, okay, to push that punching operation. So when your pressure starts to build here, okay, it would start to build in this line. Now your this valve limit is set up to say 20 bar pressure. Okay, so what would happen at 20 bar pressure, okay, at 20 bar pressure, when this entire line is 20 bar pressure, then the pressure cannot go backward here since this is a check valve here. Okay, so the pressure would come here also, it would come to this also, but relief valve is set at 180 bar pressure, so it would not open the relief valve. However, your unload valve is set at a say 20 to 30 bar pressure, then of course this will open and your low pressure pump would actually get unloaded and this would start to drain out here, okay, reservoir, right? After that, your high pressure pump would start to take over and start building the pressure. Okay, all the way up to its operating pressure of 150. So whenever 150 is there, then your punching operation is done. Now say suppose your cylinder is completely extended, okay, and your punching has been completed, but you have not pulled the lever back, okay, you have not disengaged your extending position of your DCB. So what would happen? Since this is a high pressure, it would high pressure pump, it would start building up the pressure beyond 150, because till when the cylinder was moving, it was okay, 150 was the operating pressure. The moment the cylinder got completely extended, now there is no movement that it can take place. So what happens here? Pressure starts to build. Okay, now when the pressure starts to build, again it cannot flow through this line. There is a uh, check valve here, so the pressure would start to come in this line, okay, since it's a pilot pressure itself. And if your relief valve is set to 160 bar, so the moment the pressure reaches 160 bar, what would happen? Your spool will shift upward in this case, and your relief valve will open. However, your high floor, high pressure pump will have to continue to work at 160 pressure, okay, in this circuit to drain out the system. But one advantage what you have is that you are actually protecting your system so that in no case it can go beyond 160 bar of pressure. So in that case, your system is fail safe, okay, you are protected. But again, in the relief valve case, your this pump would again consume energy, okay, to operate it at that 160 bar pressure. Okay, so this is a case in which a double pump is used both. So low pressure pump is used to initially extend the cylinder at a fast rate. Okay, the moment your actual punching it starts, then your low pressure gets unloaded, low pressure pump, and then your high pressure pump takes off, okay, to do the intended task. And again, this operation can continue again and again for different cycles, okay, to do the punching operation. Okay, so up till now we had discussion of linear actuators. So now, although I said in this entire module of your pneumatic and your electro-pneumatics or your hydraulic and electro-hydraulic, I would be focusing more on my linear motions or your linear actuators. However, just in this today's session itself, I'll be giving just a glimpse of how your rotary motor actuators or your hydraulic motors would get controlled. Okay, so what picture you have here? Okay, this is your again your power generation, then again your relief valve. This is your 4x3 DCV, spring centered, manually actuated, and this is a symbol of your hydraulic motor. Okay, so a motor with the inlet and outlet here. Okay, so that means if you are putting in your spring centered position, that means your entire ports are blocked and your motor will be remain in the stop position. The moment you engage your left envelope of your direction control valve, what would happen? Your motor would start to rotate clockwise, okay, since the fluid will enter here, okay, and it would rotate the motor in this direction and the fluid would drain from this side. Okay, so the left envelope would rotate it clockwise, and your right envelope, when you engage this envelope of the valve, okay, that means when I say envelope, that means I'm actually shifting the spool either to my left or to my right to connect different ports. Okay, so in your symbolic representation, it is known as your envelope. Okay, so in your right envelope, what would happen? Your pressurized line would get connected to this side, okay, as the arrow is here, and your motor would rotate in your opposite direction. Now, how would you do the speed control of that? So for a speed control, I actually require a flow control valve. Okay, so again, these all components, you know, this and this. What is a new component in this circuit that you can see? This one. Okay, and this is a flow control valve. What is a flow control valve? Okay, if you see the construction, it is nothing but a restricted orifice is here, in which you can actually open and close the orifice diameter through which the fluid wants to pass. Okay, and you also have in parallel, okay, a check valve here. So what does this check valve do? So during your any motion here, okay, for example, the fluid cannot flow through this path. It is forced to flow through this orifice, and if you will restrict the orifice to say to suppose 20% of the opening, then of course your motor would rotate at 20% of its speed. If you restrict it to 30% of the opening, it would rotate at 30% of the speed. Okay, right? However, when the liquid is coming back from the other side, okay, which is not the case here in case of a motor, okay, that is generally required if you are extending a cylinder and if you are retracting a cylinder. Say in the extension you require the motion to get controlled, but during the retraction, okay, you do not want the motor or you do not want the linear actuator to have any flow control mechanism. So in the retraction case, what would happen? Your circuit, if you see, it would just go and take this path. Why? This is the most easy path. Since this is the constricted path, it will have free flow from this side and just drain out. Okay, so generally this valve is a flow control valve that actually constricts the flow of the fluid through it, okay, through this orifice. Okay, and the other portion, it actually has a one-way flow valve, so that this is a block position, okay, and this is a free flow position, so that this type of valve is actually common to both your hydraulic as well as your pneumatic rotary actuators as well as your linear actuators. For the linear actuators, you actually require this circuit. In case of a hydraulic actuators, you can only do it with your orifice itself. So whenever you are going to constricting the orifice, then again the motor would rotate clockwise, okay, and the speed would get controlled through by adjusting the opening of the orifice size. Okay, so this is how you can control your hydraulic motor. After this, we will see how your hydraulic motor braking can be done. Why is this important? Hydraulic motor braking. See, a motor is a device. What? When this, if you see this motor, this will actually be coupled to something. Okay, that would make it rotate. Right? Now, suppose whatever machine it is coupled to, in which your hydraulic rotor is actually rotating that, suppose it is a very heavy machine. Okay, now if you want to stop the motor, then what would do? If you just put this valve in your center position, then what would happen? That load that this motor was driving, say it is a 2000 kg load that is rotating clockwise, okay, then that load would what would do? It would now have a flywheel effect. Have you seen a flywheel? Okay, for example, in your diesel generator sets, if you see, there is a circular very heavy object that is actually rotating. Why is it used? It is used to store the energy, right? So that internal combustion engine, it is a 4-stroke engine in which only your 1 stroke is your power stroke. The other 3 strokes, okay, is actually the energy is being fed by your flywheel, okay. Similarly, okay, that flywheel effect, what is it? Even if the your power stroke is stopped, okay, the other 3 stroke is actually your energy getting supplied by the flywheel. Similar effect you will have, okay, when you suddenly stop the hydraulic motor by putting your valve in the center position, okay, that is your all the ports blocked. So suppose the 2000 kg weight was coupled to that motor. Now even if you stop the flow of the motor, okay, now this load that was running, okay, that would try to make the rotor run, okay, and now your hydraulic rotor that was initially running as a motor, it would now try to behave like a pump, right? In a pump, what does it happen? Okay, something, an electric motor actually rotates the, okay, your pump to create a pressurized fluid, okay, and in this case, initially when you was pumping the fluid, okay, pressurized fluid, this rotor was acting or behaving like a rotor, okay, or your hydraulic motor, if you can say. The moment you stop all your pressurized liquid here by putting this motion, by putting this valve in the center position, what has happened? All these ports are blocked now, okay. Now no more you will have any a pressurized liquid either from this side or this side. Then what would happen? The load that this motor is coupled to, okay, that would start to now turn because of its inertia. It would try to still turn the motor, and now this motor will try to behave like a pump, okay, which can again lead to the, if you stop it abruptly, this would again damage the motor itself, okay. So what we do, we actually design a circuit for your hydraulic motor braking, okay. So what is the circuit? this entire component that is actually consisting of this entire circuit consisting of multiple components. If you see your check valves, okay, in specific position, this would act like a braking of the motors. Okay, so now say this was your pump, okay, and then your pump was putting a pressurized fluid from here, and then you engaged your left envelope here, so the pressurized liquid was coming here and rotating the motor in this say clockwise direction, okay, and the drain liquid was coming and getting drained here to your tank port. Okay, now the moment say your motor was running at very high rpm or anything, and what did you do? You actually instantly put your valve to the center position. Now in the center position, what is there? All your ports are blocked. That means these ports are now blocked. However, if a very high capacity load is coupled to the motor, then what would happen? It would try to rotate the motor, okay, because of its inertia. Then there has to be a system where some amount of liquid is getting absorbed to the system and being drained out, and then it will apply the brake, just like your gradual braking application. If you see something that is holding, and while the motor is still running and the motor gradually stops, okay, it does not stops instantly, it gradually stops before coming to a standstill. Okay, so in that case, what would happen? You have your system here, so you have your reservoir, extra reservoir. So the moment you close down all the ports and the motor is still running, then what would happen? Suction would start from here, okay, it would go all the way to this, come here, okay, and from here what would go? It would go all the way like this. This is a check valve place, so it can come through this, but it cannot go this side. So what would happen? Now this would come here, and this is your what? Just like your relief valve, okay, that would start to build extra pressure, okay, and then once your pressure starts to build, then this would open and your fluid would get drained out. So suppose in this type of arrangement, your motor would, hydraulic motor would come to a halt, but it will come to a halt gradually. Okay, so till when? Because that much amount of load is required to keep this circuit in motion. Now say your motor was running in an opposite direction, okay, say in this direction, anti-clockwise, then what would happen in this case? It would again take this path. Suction would start from here, okay, since this is your check valve that can has free flow in this direction, so the liquid will come here, okay, come all the way like this, drain out, go through the motor, it would go through the motor in this direction, okay, it cannot go to this port here because this is a check valve preventing it no motion from the opposite side, so it will be forced to go through this again, and then finally once this pressure has been set and this relief valve is opened, then your liquid will get drained out. So that means liquid is coming from this reservoir, okay, and then it is draining out to this reservoir, and this entire mechanism is actually applying a brake to the motor so that the motor gradually and slowly comes to a halt. Okay, in this way you can actually prevent your motor to get damaged. Otherwise, if you suddenly apply this center position and put your motors to a halt, then again, and if you do not have this type of braking system in a place, then this would lead to catastrophic failure of your motors if you have very high amount of load is coupled to your motors. And of course, in case of a hydraulic circuit, you generally have a very high amount of load because of its pretty high operating range that generally these circuits operate at. Okay, so I have more lectures, but again we'll stop it here. Okay.